Okay, so this is the completion of the probability of random variables class from Thursday. Promised the students in class that there would be one or two extra examples, problems that I would do on this video before I posted, so that those of you who weren't there on Thursday could watch it. I want to correct something that was in the other video, but I didn't want to go in and edit that. I did mention that as far as the moment generating function is concerned, in order for it to exist, what has to happen is that for some positive value b, the moment generating function itself has to be finite for all values of t less than b, and that's where I made the mistake there. I know this well enough, but I goofed. This should be for all absolute value of t less than b. We did talk about that open ball notion in class, and of course if I don't put the absolute value signs there, there's a slight problem with that, so I apologize for making that mistake. I'll just blame it on Sandy because it seems to be a good thing to do. I don't know. So again, I'm sorry for that. If you got questions, by all means, next Thursday we'll take care of that. Okay, so like I said, I'll do a couple more things here. I promised I'd do one more derivation here, and this is a good derivation to see where this kicks in. So this is the derivation of the moment generating function for a geometric random variable. So what we've got here is the expected value of e to the tx is equal to the sum. Now remember, this is a geometric, so we're summing from 1 to infinity of e to the tx times the mass function for a geometric, so that's p times q to the x minus 1. Now, when we were working in class on Thursday, we said that in the case of the binomial, we didn't have to really worry about this because as far as we were concerned, we were working with a finite set of x values going from 0 to n, and so we didn't have to worry about e to the tx blowing up on us. But the situation here is that we're letting x go to infinity, and so as far as we're concerned, q is between 0 and 1, so as x gets larger, q to the x minus 1 is going to go towards 0. And in order for this to converge, basically what's got to happen is that as fast as e to the tx is getting large, q to the x minus 1 has to be diving towards 0 so that it converges to a finite quantity here. So first, a little algebra to do. We can combine some things here. We've got e to the tx, we've got q to the x minus 1. So what we'd like to do is make this q to the x so that we have the same exponent and we can combine these. If we do that, well, one thing we can do here is we can factor out p, because that's independent of x. We need q to the x here, so we can treat q to the x minus 1 as q to the x divided by q, and that q that's in the denominator will also come out. Okay. So in the process of doing that, we still have the summation x equals 1 to infinity, and what we have left is e to the tx times q to the x. They both have the exponent x, so we combine these to be q times e to the t, all raised to the x. So now what you can see here is that we have a geometric series, and in order for the geometric series to converge, we need the absolute value of q e to the t to be less than 1. Well, we're working with t being, as far as t is concerned, e to the t is always going to be positive, and q is between 0 and 1. If it's 0, then this becomes trivial because we've got something that's certain, and we're only worried about things when they're uncertain. So as far as this is concerned, the quantity inside the absolute value bars is always positive for the non-trivial situations. So what we can basically say here is that we can drop the absolute value bars and say that q e to the t is less than 1. And essentially what we need to do now is we need to see if we can come up with a set of values of t so that we have this open ball to work with here. So we're going to solve this for t. So we've got e to the t is less than 1 over q. And then we can take the natural log of both sides, and if we do that, we've got t is less than the natural log of 1 over q. Now the question here, of course, is the natural log of 1 over q positive? Well, since q is between 0 and 1, 1 over q is going to be greater than 1, and hence the natural log of that is going to be positive. So we can also write this as t is less than negative ln q. So we found effectively our b here. This is our b over in this setting right here, and that is a positive value of b. So we know that this thing is going to converge. And since it's going to converge, we can go back to our basic geometric series rules for finding this summation. And so what we've got here is p over q times the first term. Well, the first term in this series, when x is 1, is q e to the t. And q e to the t over 1 minus the common ratio. The common ratio also happens to be q e to the t. And so we'll get this q right here canceling with that q. And so our moment generating function then for geometric is equal to p e to the t over 1 minus q e to the t under the circumstances that we had up here. And so that's that derivation. The next example that we're going to look at is our first foray into what's called a transformation of a random variable. We're going to do more with this stuff later on. I shouldn't say it's the first one, but we haven't done as much with it as we're going to do now. Essentially what we're looking for here is, suppose that we've got a random variable y, and this random variable has moment generating function m sub y of t. And what we're going to do here is we're going to define a new random variable w to be equal to ay plus b. So we're doing a linear transformation. You did see the fact that we were doing linear transformations when we were doing expected value and variance in sections 3.3 and 4.3. But we're going to take it one more step this time. Basically say, well, if we have this moment generating function of y, and we have this transformation, what is the moment generating function of w? And you may think, okay, well, I got all these summations and stuff, but Again, one thing you have to remember is that in its most basic form, moment-generating functions are expected values. So we can use the rules for expected values the way that we did in sections 3.3 and 4.3. So the moment-generating function of w is equal to the expected value of e to the tw. But we have the fact that w is equal to ay plus b, so we can go ahead and make this substitution in the expected value here. So this is equal to the expected value of e to the t times the quantity ay plus b. Now, before we use any of the rules for expected values, the other thing that we can do here is go ahead and multiply out, distribute the t. So this becomes the expected value of e to the tay plus tb and as you recall, if you're adding exponents with a specific base, that means that you're multiplying two quantities that have the same base. So this also becomes the expected value of e to the tay times e to the tb. Now we can start to go back and use those rules from sections 3.3 and 4.3. The thing to recognize here is that we've got the expected value of a product, and we didn't really do a whole lot with expected values of a product in that case. Basically, the only thing that we saw there was the ability to pull constants outside the expected value. Well, the thing to remember at this point is the fact that our random variable is y. Everything else up there is a constant, and so as far as we're concerned, this piece right here, e to the tb, is a constant with respect to y, so that can be pulled outside. So that, oops, too many e's. So this becomes e to the tb times the expected value of e to the tay. Okay, so times people look at this and go, what the heck do I do now? Well, if you take a look at this form right here, this is very similar to this form right here. Now we're in terms of y. So in this case, right here, this is the moment generating function of w with respect to t. Okay, that's your argument right there. Here we have the moment generating function of y as a function of t. So the way that we look at this is that this piece right here is our constant in this situation. So this becomes e to the tb times the moment generating function of y evaluated at ta as opposed to just t. So, to give you an example of how that works, let's go back to the geometric case that we did before this, and I'm going to leave that right there. So let's say that we've got a variable y, it's geometric, with the value p being equal to 0.2. So since we've got something that we know is geometric, we can write its moment generating function. What we have is my of t is equal to, remember the numerator is p e to the t. So we have 0.2 e to the t, and then in the denominator it was 1 minus q e to the t. So this is 1 minus 0.8 e to the t. And we have the restriction that t has to be less than the negative natural log of q. So the negative natural log of 0.8, that's our region of convergence. Okay. So we're going to define a new variable. We'll call it w. And let's say that we've got the transformation w is equal to 4y plus 7. So in this setting, a is 4 and b is 7. So to get the moment generating function for w, this is going to be e to the 7t, remember e to the tb over here, times the moment generating function of y evaluated not at t, but at 4t. Remember the 4 is coming from a here, and t times a right here. So now we're going to go ahead and make our substitutions back up here. So we need to take e to the 7t, and then everywhere in our moment generating function of y where we had t, we need to replace it with 4t. So this becomes 0.2 e to the 4t over 1 minus 0.8 e to the 4t. And we now have the moment generating function of w. Okay, so that's the last example for this. Again, depending on when you're watching this, have a good weekend or good next week. I'll see you next Thursday at the latest. And by all means, please remember to go out and vote. It's a very important thing to do for all of us in this country. So anyway, take care, and I'll see you next week.